cuando empiece Juli. Por favor.
Ya está. We're online.
Okay.
Listo, Rita.
Okay, so thank you. So the name of the organizer committee, I like to say, everybody, good morning, buenos días, dzień dobry. We like to say thank you to all our invited speaker and the rest of the participants to this CART 23. In this occasion, we plan to have a very nice trip from Mexico, Poland, Malta, and Spain. So enjoy it. Now is time to start with our first invited speaker, which is Cesar Hernández. I met Cesar many years ago when he was a PhD student. And I was very surprised because in this time, Cesar was an unusual PhD student because really he has a very big production independent of his PhD thesis. He teaches a lot, he has a lot of bachelor students. So he's really extraordinary. And then today for me is a honor, and I am really very happy that I can introduce Cesar like my colleague of in the Faculty of Sciences, Science Faculty of UNAM. So, Cesar, the time is yours. Thank you.
Thank you very much, Rita. Thank you very much for the really nice introduction. It's not that many years ago. We are both younger than we appear. So let me start by sharing my slides. So, is everyone seeing my slides okay right now?
Yes, we see your slides and we hear you correctly.
Perfect. Thank you very much. So just let me get a timer for myself. Today I'm going to talk to you about a common generalization of bipartite graphs and split graphs. But before that, well, just this is joint work with a number of my PhD students, mainly with Fernando Esteban Contreras Mendoza, but also some of the work of other of my PhD students and also bachelor students has to do with this subject. And I know that most of you already know graph theory, so I will just skip the basics, but I will start with some definitions that might not be very common. They probably are very common in Poland, but maybe not so in Mexico. So I would like to define a hereditary property. So we say that a property of graphs, well, to begin with, we will think of properties of graphs basically as sets of graphs. And here we have a simple example. When we said that we consider the property of graphs being connected, the property, we can have the property of a graph to be connected. And if we ask, which are the graphs that have this property, and we can think that exactly as the set of all connected graphs. So basically, testing for a graph to be connected or not is basically testing for a graph to be in this set or not. So we will think of properties of graphs both as sentences in logic describing some property that the graph can have, but also at the same time as the set of all the graphs having that given property. So we have two examples here. One of them is the property of a graph being connected, and we have an example, K3. And we also have another example, in this case, of a hereditary property. A property is hereditary if it's close under taking inducible graphs. And as an example of a hereditary property, we considered empty graphs, the property of being empty, and it's not having any edges. Then we can see that if we take an induced subgraph of an empty graph, for example, these 4 red vertices, I'm going to delete them. If I delete them, then again, we end up with an empty graph. So by looking at this example, we can convince ourselves that the property of being empty is a hereditary property. On the other hand, we can see that not every property is hereditary. For example, if we, instead of K3, consider P3 for the case of connected graphs, then we have that if we delete this red vertex, then we end up with 2K1, which is not a connected graph. So the property of being connected is not a hereditary property. So there are properties that are hereditary, there are properties that are not. We will only consider hereditary properties in this talk. And a couple of simple observations about hereditary properties. For example, since K1 is an induced subgraph of every graph, then K1 has every possible hereditary property. So we could say that the smallest possible induced subgraph of any graph has any property that you like. So what can we say about graphs that doesn't have a given property P? Since now we know that the smallest induced graphs will always have the property. Well, we can start testing, and we can say for every possible vertex. We know that the total doesn't have the property, but we can try and check which of its induced graph have the property P, and to do that we can proceed algorithmically and kind of check each vertex if it can be removed from the graph. For example, we consider this vertex and we remove it. And if we remove it and the resulting induced graph still doesn't have the property, we get it out of the graph and forget about it. But if at some point we remove a vertex and then the resulting induced graph do have the property P, then we don't remove it. And if we do this check for every possible vertex in the graph, then the remaining graph that we will have is a graph that doesn't have the property P, but such that every induced subgraph has a property P. We will call these kind of graphs minimal obstructions for property P, because whenever we have a graph that doesn't have property P, we can use this construction and get a graph with this property. The property that it doesn't have the property P, but every induced subgraph does. Every proper induced subgraph does. So from this point of view, we can see that hereditary properties can be characterized in terms of its minimal obstructions. A graph has a property P if and only if it doesn't contain P minimal in obstructions as induced subgraphs. So this is a good thing, because there is a characterization of every possible property in terms of some set of induced forbidden subgraphs. Let me say a bit more about minimal obstructions. If you have any property and you define the complement of the properties as all graphs such that the complement of that graph has a property P, and let me put you a simple example. Then, for example, the complement of the property of being empty is the set of all graphs such that its complement is an empty graph, but that's equal to the set of graphs such that are complete graphs. So in general, we can extend this the observation in this simple example to say that if we forbid a set of minimal obstructions, and we consider all the complements of those minimal obstructions, then we are actually characterizing the complement of the property that's being characterized by this set of minimal obstructions. Let me put some more examples regarding hereditary properties, and we will see this duality here in some of these examples. For example, we already mentioned empty graphs. They have only one minimal obstruction, which is K2. Complete graphs have only one minimal obstruction. Since empty graphs are the complements of complete graphs, then the only minimal obstruction for empty graphs must be the complement of the only minimal obstruction for complete graphs. So the only minimal obstructions for complete graphs is 2K1. Something similar happens with multipartite graphs. We know that a graph is complete multipartite, A graph is complete multipartite if it can be partitioned into some independent sets such that each vertex in one of the independent sets is completely adjacent to the vertices outside its independent set. And it's a well-known result that this family is completely characterized by disjoint union of a K2 and a K1. This might not be completely obvious, but one thing that it's more obvious, and it's actually a common exercise in any undergraduate graph theory course, is that if you forbid P3, then the set of all graphs that doesn't have P3 as an inducer graph is exactly the set of graphs such that every connected component is a clique. So this is basically a disjoint union of complete graphs. And it's easy to see that the complement of that disjoint union of complete graphs is precisely a complete multipartite graph. So again, we have this duality when we take complements. One fifth example, is the class of split graphs. Split graphs are precisely the graphs that can be such its vertex set can be partitioned into an independent set and a clique. And these graphs are characterized, they have a beautiful characterization with only 3 minimal obstructions, which is C4, 2K2, and C5. And you can see that if you have a split graph, then the vertex set can be partitioned. One independent set, one clique. If you take the complement of a split graph, the independent set becomes a clique, and the clique becomes an independent set. So basically, the complement of any split graph is again a split graph. And you can see that property from its set of minimal obstructions, because the complement of C4 is 2K2. Naturally, the complement of 2K2 is C4, and the complement of C5 is C5 again. So basically, what we are saying is the set of minimal obstructions is close undertaking complements, and that has as a consequence that the property itself is close under complements. That will also be true in general, which is a really nice property that you can notice by just looking at the minimal obstruction. So another reason to consider hereditary properties. Last example, very well-known example. If G is a bipartite graph, then the set of minimal obstructions is precisely the set of odd cycles. Everybody knows that a graph is bipartite if and only if it doesn't contain odd cycles. So what are we going to use these minimal obstructions for? We're going to use it as no certificates from a given set of algorithms that are known as certifying algorithms. And just to put a bit into context of what a certifying algorithm is, let me remind you that what a decision problem is. A decision problem is just a problem that you can put in terms of a yes-no question. Basically, a typical decision problem, I will take an object, for also obviously a mathematical object, and I will give you the object and make you a question about the object. For example, the problem is bipartite. The input, the object we will be dealing with, is a graph. So basically, I will give you a graph, and I will ask you a question about this graph. And the graph is is this graph bipartite? Naturally, this is a yes/no question. The graph is either bipartite or non-bipartite. So this is the kind of problems that we want to solve with our algorithms. We want an algorithm so that receives a graph as an input and answers yes or no, depending on the fact that is the bipartiteness of G. So what's the problem with this kind of algorithms? The main problem is that one of these algorithms, of course, we want to implement it in real life. We want to choose a programming language and make a program that will implement these algorithms. So we can take a graph and turn it into an object in the programming language, and then run it through the algorithm. And the algorithm, if the algorithm only outputs yes or no, then how do we know if the algorithm is correct? If we, for example, have a graph on, I don't know, 5 vertices, then if the algorithm is not correctly implemented, then we can see that there's a mistake, and we can see that, for example, that a graph that is not bipartite receives the answer yes, or vice versa. But if we're considering a graph that has thousands of vertices, and we run this algorithm and it only answers yes or no, and we have doubts about that this algorithm is well implemented. For example, if I implement this algorithm, I will have doubts that it's correctly implemented. What if I made a mistake? Then one thing that we can do to get rid of doubt is make the algorithm into a certifying algorithm. That will be, it doesn't only answer yes or no, but it also gives you certificates. A certificate is just an object that will help you convince yourself that the answer is correct. And for example, in this case, for bipartite graphs, we know what would be a good certificate. We would have 2 kinds of certificates: yes certificates and no certificates, depending on the answer of the algorithm. What would be a good certificate? The bipartition of the graph. If the algorithm responds yes and also outputs a bipartition of the graph, then we can easily check, of course, also computationally, but easily, that the given partition is in fact a bipartition. Basically, we only have to check that vertices in the same set doesn't have neighbors inside the same set. So that amounts to basically checking the neighborhood of each of these sets that we have, for example, as a list of vertices, and that's easy to do. Or as a no certificate, the algorithm could return an odd cycle. And basically, there is a certifying algorithm that does this, and probably most of you know this or have seen this algorithm before. Basically, you just perform a BFS search, starting in any vertex you want, and you start coloring vertices, red and blue. The root is colored red, and all its neighbors are colored blue, and then the neighbors of its neighbors are colored red, and you go on. And what will happen? One of the 2 possible options. Either when you're exploring one blue vertex, for example, you will find a blue neighbor of that vertex that, because of the properties of BFS, will be in the same level as that vertex. And then you can go up and find their least common ancestor, and you will find a path from each of the vertices to the least common ancestor together with the edge that joins them, and that will be an odd cycle. In that case, you can return the odd cycle as a no certificate. And if this never happens, then all vertices colored blue won't have edges between them. All vertices colored red won't have edges between them. And basically, you can return the blue vertices and the red vertices as a bipartition. And you can do that basically in the same time as the execution time of BFS, which is basically linear on the number of vertices and edges of the graphs. So it's really nice. We have a linear certifying algorithm to determine whether a graph is bipartite or not. There's also a similar in the fact that it's also certifying and linear, but it's not based on BFS necessarily, certifying algorithm for recognizing split graphs. Actually, the first such algorithm was found in 2004 by Hale, Klein, Nogueira, and Proti. But 3 years later, there was a nice upgrade to this certifying algorithm. And Hegerns and Cratch prove that if you have your graph and the adjacent lists of each vertex are ordered with some total ordering of the vertices of the graph, then again the G certificate can be checked in linear time, but no certificate, which are basically 2K2, C4, or C5, basically the minimal obstruction for split partition, can be checked in constant time, which kind of makes sense because you have no certificates with constant size. They either have 4 vertices and 4 edges, or 4 vertices and 2 edges, or 5 vertices and 5 edges. So that should not depend on the size of the input. That should be something that can be done in constant time, and it's actually possible to do that. So these are really nice algorithms. And basically, what we know so far is that determining if a graph can be partitioned into 2 independent sets, basically a bipartite graph, is an easy problem. We have a linear time certifying algorithm to solve that problem. Partitioning into 1 independent set and 1 clique, it's also easy. That is basically the certifying algorithm to identify split graphs. But we know that partitioning into 3 independent sets is a hard problem. It's an NP complete problem, actually, because this is 3 coloring. And 3 coloring is equivalent to 3 co-coloring, that it's partitioning to 3 cliques. So basically, keep in mind this thing we mentioned about taking complements. So identifying partition into 3 independent sets should be the same as identifying partition into 3 cliques. So there's a jump in complexity. Identifying 2 independent is easy. 1 independent, 1 clique is easy, but identifying 3 independent is hard. So a really natural question is, what happens if we have 2 independent and 1 clique, or 2 cliques and 1 independent set, which is basically the same problem. This kind of graphs, the graphs having a partition of this kind, are called 2-1 colorable graphs, and such a partition is a 2-1 coloring of the graph. And in 1996, Brandstadt proved that these graphs could be recognized in cubic time. But a couple of years later, he noticed, and actually published this corrigendum, that this algorithm was not correct. And we can see something here. If you see the second paragraph, polynomial times algorithms with worse time bounds for recognizing 2-1 graphs and 2-2 graphs are described in some technical reports. Those technical reports talk precisely about this algorithm. Considering that M is the number of edges, and that could be quadratic in the number of vertices, then this could be something of the order of n to the 4th. So this is not a very nice algorithm. People working with real-life applications would say that only quadratic is kind of good in real life. So n to the 4th is by no means good. But okay, this is the algorithm that it's known. But also, this algorithm produces a 2-1 coloring, but it doesn't provide no certificates. On the other hand, there's a n to the third, a cubic algorithm using a technique developed by Hale, Klein, Feder, and Modwani that use is called sparse dense partitions. That theoretically is beautiful, but it's not easy to implement. And as it is, the algorithm is not a certifying algorithm, although it seems possible to modify it into a certifying algorithm, but it would be even harder to implement it in that sense. So we would like to know if there is a better solution to this problem. Is there an easy to implement certifying algorithm to recognize 2-1 colorable graphs? And of course, a valid question is this algorithm, or if such an algorithm exists, can we find a linear time algorithm that does this? This problem, of course, looks to be really, really hard. So we would like to study some restrictions of it before trying to solve the general problem. Of course, it's hard, but it might be doable. It's not like trying to prove if decide if P equals NP or something like that. This is something that we already know that there's an algorithm to solve, and the algorithm is polynomial, it's cubic, or n to the 4, depending on which approach you like. And basically, the question is if we can make a better algorithm out of this. So we will consider like a general setup for our problems. This general setup is a setup called matrix partitions. And matrix partitions generalize many different problems when partitioning the vertex set of a graph. For example, by partitioning into independent set can be represented by this matrix. Basically, we're saying each 0 in the diagonal means an independent set. Each 1 in the diagonal means a complete graph, a clique. And we basically are saying we want to partition the vertex set of our graph into 2 independent sets without further restriction between them. This is basically, we want to determine if our graph is bipartite or no. In the second example, basically, we want to partition the vertex set of our graph into an independent set and a clique. In the third example, this is 3 coloring. And we have some additional restrictions that we can place. For example, here in these 3 cases, outside the main diagonals, we only have asterisks, meaning that there are no further restrictions. But for example, here we have the definition of a probe split graph. A graph is probe split if it admits a partition of this kind of matrix. And we are basically saying we want to partition the vertex set of the graph into 2 independent sets and 1 clique, such that the clique is completely adjacent to one of the parts of the independent set, meaning that every vertex in the clique is adjacent to every vertex in one of the 2 parts is completely adjacent to one of the 2 independent sets. The same independent set, by the way, not any of them, but one of them. And we can see, for example, that probe split graphs generalize bipartite graphs, because if the third part is empty, then we basically have this 2 by 2s of matrix, that is the matrix corresponding to bipartition. And if this middle part is empty, then we have 0, asterisk, asterisk 1, which is a matrix for split graphs. So probe split graphs generalize both bipartite graphs and split graphs. And it is known that there is a cubic, again, algorithm to verify whether a graph admits a probe split partition. And it provides yes certificates, but it doesn't provide no certificates. And probably the reason that it doesn't provide no certificates is that there are 49 graphs and 3 infinite families of minimal obstructions. And basically, these are like the natural no certificates that one would want to provide in a recognition algorithm. So the authors were not really trying to get a certifying algorithm. So while they're doing this construction of the probe split partition comes naturally from the proof that these are exactly the minimal obstructions, but they were not thinking of producing the certifying algorithm. Maybe this algorithm can be turned into a certifying algorithm, but maybe it's also easier to like make a completely new proof and try to get the algorithm from this new proof. Another family of graphs that has been studied a lot in the literature is the family of 2-1 polar graphs. A graph is 2-1 polar if it can be partitioned into, you can see that is one click and one complete bipartite graph. We can say that into three sets, such that 2 of them are independent, one of them is a click, and the 2 independent sets are completely adjacent. That would be another way of saying this. So far, there are no simple characterizations for 2-1 polar graphs in general. We are working on a characterization by forbidden minimal obstructions, and so far we found, I think, something between 42 and 47 minimal obstructions, and probably they're not all. We think that we'll still find a couple more in the future, but we are working towards a characterization and a recognition algorithm. But actually, when you restrict the problem of recognizing 2-1 polar graphs to cographs or chordal graphs, the minimal obstructions are easy to describe. I think that for cographs, there are 7 minimal obstructions, and for chordal graphs, maybe something around the same number, maybe 5 or something like that. So I would like to say that these problems are kind of simpler problems that well, probably not simple, because there are at least 40-something minimal obstructions, but problems that you can approach in some way. Okay, so if we want to solve these problems, again, you can see that, for example, split partition is a subproblem of this problem, because we have here as a subproblem or as a submatrix of this matrix, the matrix corresponding to split partition, and we also have the matrix corresponding to bipartite, complete bipartite graph. So it would be a good idea to know the minimal obstructions and also algorithms to recognize the graphs admitting M partitions for smaller patterns M. And we know that, for example, all M2 by 2 patterns, all M2 by 2 matrices correspond to some of these 6 problems or its complements. So basically, if you solve this, you can solve all the matrix partition problems for 2 by 2 patterns, and it's already known that all of these have linear certifying algorithms. We have talked about the linear certifying algorithm for bipartite graphs and for split graphs, but we have other cases that can also be recognized by a kind of simple linear time algorithm. I say kind of simple because we have a couple of cases here that I say BFS on complement, BFS on complement. There's a way of executing BFS on the complement of a graph without explicitly calculating the complement, because that would take quadratic time and it would be linear no more. But this is simple, but not as simple as one would like. And when we were looking at this, particularly when we were looking particularly at complete bipartite graphs, we say, okay, we notice that you can apply BFS on the complement, and then you recognize basically a graph such that every connected component is a click. That should be easy using BFS. But what if you have what if you want to recognize a larger complete multipartite graph? And we start looking at literature for algorithms for complete multipartite graphs to recognize them, certifying algorithms, and notice that there are no easy to implement and using simple data structures algorithms to recognize complete multipartite graphs. So one first thing we did was to propose a simple algorithm based on BFS, loosely based on BFS, to recognize complete multipartite graphs that work in general for not only for bipartite, for complete bipartite, but for complete multipartite in general. So the idea, I will tell you about this algorithm next, but we need to keep track of a couple of things. The first vertex that was colored with any given color, and also the first vertices that were colored to the last two colors that we use in our algorithm. If we keep track of these three things, then we can perform the following algorithm kind of easily. So we start with any given vertex, and as if we were performing a regular BFS, we enqueue all of its neighbors. And we color the first vertex with a given color, in this case green. And we don't know the color that its neighbors will have. But when we expand one of its neighbors, we know that this neighbor should have a different color. So right now, A is a root, and B is this vertex that is circled in red. This is the first color that was colored green, and the first color that was colored blue. All the neighbors that are neighbors of this second vertex, of B, but are no neighbors of A, are non-adjacent to A. So if this is a complete bipartite graph, then all of these vertex should have the same color as A. So we color all of them green. Things can still go south, and this could be not a bipartition, but we will identify that later. So we keep on, this vertex can also have some neighbors in the neighborhood of the root vertex. In that case, what we'll do is we'll change the parent of these vertices, and now the parent of these vertices will be this new vertex. Basically, what are we saying? We're saying is that these vertices are neither colored green nor colored blue, because they are adjacent to at least one vertex, and they are adjacent to at least one blue vertex. So we will keep this problem for the future to determine which color is each of these vertices, and we will keep on processing the remaining vertices. So what happened at this point? At this point, we have processed one green vertex and one blue vertex. If we are thinking of a complete multipartite graph, we know that in the neighborhood of these two vertices, we must have seen the whole of the graph, because otherwise there's an explored vertex somewhere. This is an explored vertex, and this vertex together with this edge, since this is not a neighbor of any of those, we found K2, a disjoint union of K2 and K1, which is a minimal obstruction for a complete multipartite graph. So at this point, if there are still unexplored vertices, we construct this minimal obstruction and return it as a no certificate. Otherwise, we keep on processing the vertices. The next neighbor of the root vertex is this one, and since we didn't process it while processing the vertex B, this first blue vertex, then this is not adjacent to vertex B. So we can give it color, the same color as B, in this case is blue. And we continue. And for example, if we try to color an already colored vertex, what could happen? One thing that could go wrong is that it could be adjacent to another vertex that is already colored and it has its same color. But in this case, what will happen is that these two vertices are non-adjacent to the root. Otherwise, we wouldn't have given them the color green. So we know that these two are adjacent and both are non-adjacent to the root. So basically, again, we can construct a no certificate and return it. And just to, I think this is the last case, if an uncolored vertex is active, when we process an uncolored vertex, what happened is that it will receive a new color because it's adjacent to a green vertex and it's adjacent to a blue vertex because it's an uncolored neighbor of the blue vertex, of the B vertex in this case. It will receive a new color, and its uncolored neighbors are either a children of A, like in this case, in which case we can give them the same color as B. They are uncolored because we didn't find them when processing B. So basically, they are non-adjacent to B, and we can give them the same color as B, or they can be children of B. And in this case, we just save the problem for later, and we give them a new parent, which will be this new color. In this point, every green vertex and every blue vertex has been found, and basically we can change the active vertices. Now B becomes A, this new vertex becomes B, and then we can iterate. And we can repeat this process, and we will be discovering all the color classes or all the independent sets in the complete multipartite graph by repeating this process. And basically, the idea is that at each point we discover a new or we complete a new color class and continue with the next color class in the next iteration. So basically, this is the idea. And a quick analysis of the time. With one linear pass, we can check if the graph is empty. In that case, it's complete multipartite, and we return it as a yes certificate. Otherwise, with one linear pass, we can color the graph as I just described. But what happened is that something could go wrong, and if something could go wrong, then I probably would need two additional linear time passes to construct the complement of a P3 that I also show you how to construct some no certificates and return them. But you can see that in any case, a total linear time is used. And as also you can see, you don't need any complex data structures to implement it. Basically, you need a queue and you need a couple of arrays, and that's it. So using only elementary data structures that are basically already implemented in most of the programming languages of your choice, you can easily implement this certifying algorithm. Okay, so getting back to the main problem, 3x3 matrices. We classified every possible matrix into two kinds. The ones that have only zeros in the main diagonal, and from this case, only these two are interesting. I will take later a bit the one on top, the middle column. The one on the third row in the first column, we're also working on that with some of my former PhD students and postdocs. Again, so far, we've found a lot of minimal obstructions, and actually, we know what the minimal obstructions are for the case of chordal graphs, but the general case still needs some work. But the really interesting case is the case when we have mixed diagonal. Because in a mixed diagonal, this graph T is precisely 2-1 coloring. And we can put further restrictions. And the more we restrict the problem, the easier it gets. So what are still open problems here? Or what is known about these cases? It is known that for this last pattern, these are 2-1 colorable graphs. D1 and D3 correspond to 2-1 polar and probe split graphs. D2 is a weird case Up to our knowledge, it hasn't been studied before in the literature, and we have been working on these two and find several infinite families of minimal obstructions. So D2 seems to be a hard problem, but we are optimistic that we might find a way to describe the minimal obstructions, but we think that it's really hard to explicitly say what the minimal obstructions are. So basically, working in this object, the main result so far is that we have found minimal obstructions for all the other problems. That is basically all the patterns having only one asterisk of the main diagonal, together with the pattern that I mentioned that has 3 zeros in the main diagonal, the one of the two that are interesting. And for all these families 1 to 6, we have linear time certifying algorithms. For 7, the problem is that there are a lot of minimal obstructions, something like 37, if I recall correctly. We don't have a linear time certifying algorithm for this yet, but I strongly suspect that one exists. If I have time later, I will tell you why. But let me tell you quickly about how one of these proofs are done. Basically, the idea is that you can read the minimal obstructions, and minimal obstructions tell you something about the graph. You can see that all these minimal obstructions have a triangle, and basically they tell you how other vertices in the graph interact with the triangle. And we are saying that some interactions with the triangles are forbidden. This is what this is saying. So basically, for the proof, consider a maximal click. Get a click and get one that is maximal. It is not properly contained in any other click. And we will check the adjacencies of each other vertex to this vertex K. And what happened? If you have a vertex that is adjacent to some vertices, but not all of them, and not only one of them, then you will have this as an inducible graph. So that means that every vertex is adjacent, every vertex not in K is adjacent to only one vertex in K, or all vertices in K but one. And what happened to the vertices that are adjacent only to one? All of them should be adjacent to the same vertex. Otherwise, you would have the bull or the house as an inducible graph. So basically, vertices that are adjacent to just one vertex or a click are adjacent to the same. Something similar happens to the vertices that are adjacent to everything but one vertex. Because if they don't share the vertex they are not adjacent with, you will have one of these two, the gem or the four-wheel, as an inducible graph. You can see here the gem, or if this edge is present, you will have the four-wheel. So basically, we have that so far, vertices that are adjacent to only one vertex in K, or to all but one vertices in K, and they share the same neighbors inside K. Moreover, between these two kinds of vertices, they don't share neighbors, because if you have a vertex that is adjacent to everything but one, and one vertex that is only adjacent to one of the same neighbors of this vertex, you will have this vertex here, the dart, as an inducible graph. So basically, we have 3 subsets of B. The vertices that are adjacent to no vertex in K, or the vertices that are adjacent to only one fixed vertex in K, or the vertices that are adjacent to every vertex in K except for this fixed vertex. So we want to construct the A6 partition. So basically, we want to check some independencies and some complete adjacencies. In this case, we can see that if S0, the vertices non-adjacent to the click, doesn't form an independent set, then we can find K2 plus K3 as an inducible graph. If S1 is not an independent set, we can find the hourglass or butterfly as an inducible graph. And if S2 is not an independent set, then we can find this subgraph here as an inducer graph. So basically, S0, S1, and S2 are independent set, but moreover, the union of S0 and S1 is also an independent set, because if we have an edge between S0 and S1, then we will have this graph as an inducer graph here. So basically, what we have is that S0 union S1 is an independent set. S2 union, this fixed vertex, is also an independent set. And K minus this vertex is an independent set which is completely adjacent to S2 union U. So basically, this is an A6 partition. So this is like the way that these proofs are usually made. You read the obstructions and think what this obstruction is telling me about the interaction of some particular part of the graph with the vertices outside that part. So in the last 2 minutes, I want to tell you that this proof also produces a linear time certifying algorithm. Basically, what we do is one sweep of BFS tells us if the graph is bipartite or an odd hole or a triangle, or has a triangle. If it's bipartite, we are done. We return the bipartition as a yes certificate. If there's an odd hole, we return the odd hole as a no certificate. And if it's a triangle, we make one additional sweep to extend the triangle to K, to a maximal click. That's easy to do. One additional sweep will tell you for each vertex if it's an S0, S1, or S2, or if it's in none, we can construct a minimal obstruction and return it as a no certificate. And with one more sweep, we can check the no adjacencies. We can check that S0 is an independent set, S1 is an independent set, S0 union S1 is an independent set, and S2 is an independent set. If one of these fails, as in the proof, we construct a minimal obstruction and return it as a no certificate. Otherwise, the end of the proof tells us which is the A6 complement partition, and we return it as a yes certificate. So basically, final remarks. I've already mentioned this in the talk, so I will not stop here. But basically, the problems we have still open are 2-1 polar graphs, 2-1 coloring, of course, and finding better algorithms for probe split graphs. And we think that at least for 2-1 polar and maybe probe split graphs, it might be possible to find linear time span and space certifying algorithms. So that will be all. Thank you.
Ponerme en la cámara. I am trying to put my camera.
I will stop sharing so we can see if anyone asks any questions.
Okay. Sorry. Did you hear me, Cesar?
Yes, yes, yes.
Yeah. Okay. I don't know. I have. Okay. Now, okay. Thank you very much for your talk. I'm sorry. I have really problems with this internet here. So I don't know if somebody has any question. Let me to check the. Okay. We have one of Bruno. Can you see the chat?
What kinds of families of graphs can be expressed using that matrix notation? Well, a lot, but for example, one nice example that tells you about the expressive power of this notation is homomorphisms. Every matrix that only has zeros and asterisks corresponds to a homomorphism problem. And for example, if you don't have asterisks at all, if you have only 0-1 0-1 entries, you have full homomorphisms. That is basically you take a graph and you blow up every vertex into either an independent set or a clique. And basically that admits a full homomorphism to the original graph? Well, you have to take care of the loops, because you can only blow up vertices having loops to clicks, but these are kind of problems that can be expressed using matrix partitions. Okay, I can also see that Hannah has a question.
Thank you. I think Hannah has a...
Yes, I would like to ask you about one thing. First of all, I would like to say thank you, because I like such algorithmic approach very much. So thank you very much for your talk. And I have a question according the 2-1 coloring.
Yes.
Sometimes it's desirable to fix the cardinality of color classes, color sequence or something like that. Do you know any papers, any such approach that the problem of 2-1 coloring is considered, but plus some considerations about cardinality of color classes?
No, I heard about it, but I've never seen someone that works with that approach. One good question is if it's still a hereditary property, and I think it should. But no, sorry, I haven't seen any such approach in the literature.
Okay, thank you.
Thank you.
I don't know if we have more questions, comments. No, by the moment, but I invite to everybody that have any question, any comment, you can contact directly Cesar or with us. So thank you very much again, Cesar. Very nice talk. Thank you very much. And now we will continue with the next talk with Iwona. So, Nate?
You hear me?
Fine.
Yes.
Hello, everyone. It's a pleasure for me to introduce to Iwona Włoch. Since 2016, she is an associate professor at the Department of Discrete Mathematics in the Faculty of Mathematics and Applied Physics in the Resistową University of Technology, Poland. Since 2020, she is a vice rector for education. Her main research topics include domination and independence in graphs, Fibonacci types, sequence, and hypercomplex numbers. Thanks, Iwona.
Thank you very much. It's a great pleasure for me to say something about dominating set. I would like to thank the organizers for Rita and for inviting me. And in my talk, I would like to say about the special type of dominating sets in graphs, namely about 1-2 dominating set. We start with some definitions and notation, and next we describe parameters related to 1-2 dominating set, and in particular I would like to say about 2 variants of 1-2 dominating sets, namely proper 1-2 dominating sets and perfect 1-2 dominating sets. Sorry, I have a small problem, but I try to maybe in such way. Okay, we start with the basic definitions. A subset G is a dominating set of a graph G if for every vertex not belonging to the set G, there is a vertex in the set G such that X and Y are adjacent. For example, let's consider the following graph. And if we indicate vertices C, F, and I, then these vertices belong to a dominating set of this graph because every black vertex is adjacent to a green vertex. And with a dominating set, we can connect special graph parameters, namely dominating number and an upper dominating number. A dominating number of a graph is the cardinality of the minimum dominating set. And in our graph, we can observe that a dominating number is equal to 3, because we cannot find a dominating set of the cardinality less than 3. And in graph, we can consider also another type of extremal dominating set, namely minimal dominating set. And we say that dominating set is minimal if every its proper subset is not dominating. And we define an upper dominating number of a graph as the cardinality of the maximum minimal dominating set. And let's consider our graph. For example, here we have green vertices, which belongs to a dominating set, because every black vertex is adjacent to a green vertex. And we also can observe that this set is minimal dominating set, because we cannot delete any green vertex from our set. But we can ask about maximum minimal dominating set. We can find maximum minimal dominating set as here. A, B, D, F, H, I, and K belongs to the maximum minimal dominating set, and our graph parameter is equal to 7. So in the literature, we can find a lot of papers related to the topic of domination. There are a lot of kinds and variants of dominating sets. And one of well-known type of domination is multiply domination, introduced in 1985 by Fink and Jacobson. I recall this definition because this type of domination is connected with our topic. Let K be an integer, and we say that a subset D is a K dominating set of a graph G if for every vertex not belonging to the set G, there are at least K adjacent vertices in our set. For example, if K is equal to 1, then you obtain the classical definition of dominating set. If K is equal to 2, then you obtain the definition of two dominating set. And if we consider the following path, then vertices which are marked by green color indicate two dominating set, because every black vertex has two adjacent green vertices. The topic of two dominating sets, also named as double dominating sets, is well known. And two dominating sets are studied with respect to different directions. For example, with respect to parameters related to dominating set, or sometimes also with additional restrictions such as independence. And we can find many interesting papers in which two dominating sets and so-called two dominating kernels are studied. Here we have some selected papers related to two dominating sets and independent two dominating sets. And quite recently, also a general concept of K-dominating independent sets was studied by Notch, but we can observe that if K is an arbitrary or a fixed integer, then vertices not belonging to K-dominating set have to have a large degree. So it's natural is to consider first the two dominating sets. And in my main topic of this talk, also distance dominating sets relate. So I recall this definition. Let L be an integer. A subset D is a distance L dominating set of a graph G if for every vertex not belonging to the set D, there exists a vertex in this set such that the distance between them is at most L. If L is equal to 1, then you obtain the classical definition of dominating set. And here we have two simple examples of graphs. In the first cycle, we indicate a subset of vertices, which is a two dominating set, because every black vertex is at the distance to a green vertex at the distance at the most 2. For example, here we have the distance 1, and for this black vertex we have the distance 2. In the next case, we indicate the classical dominating set, so-called one dominating set. And if we consider multiply domination, in particular two domination and distance domination, then these two concepts of domination can be joined with a special case, special variant of dominating sets, namely 1K dominating sets. And such a mix of domination was introduced by Hedetniemi and other in 28 when they introduced so-called 1K dominating set. I recall this definition because in the next part of my talk, I will say about this type of domination, in particular for K equals 2. But clearly, I give the general definition. Let K be an integer, and we say that a subset D is a 1K dominating set of a graph G if for every vertex not belonging to the set D, there are two different vertices, say U and W, such that one of them is adjacent to our vertex V, and the second is at the distance at most K. We can say that the definition of one K dominating set is a weaker version of two dominating set because the second vertex is not necessary in dominating set. It suffices that it's at the distance at most K. And if K is equal to 1, then we obtain mentioned earlier the definition of two dominating set. So the next case if K is equal to 2, then we obtain the concept of 1-2 domination. Analogously, as for dominating sets, we define parameters being 1K dominating number and upper 1K dominating number. I recall that 1K dominating number is the cardinality of the minimum 1K dominating set, and upper 1K dominating number is the cardinality of the maximum minimal 1K dominating set in the graph. As I can mention, a two dominating set is well known and intensively studied. So in my talk, I say about results related to 1, 2 dominating number. Here I will list selected paper related to the concept of 1, 2 dominating sets, and presented results in the next part of my talk are obtained mainly with Adrian Michalski and Magda Dedlaw and Magda Lemańska. And recently, some interesting results were obtained by my colleagues from our university. I will say about it in the next part of my talk. Let K be an integer, and suppose that K is less than L. Then every 1K dominating set is 1L dominating. So to observe this relation, let's consider the following path. Then green vertices belongs to the 1-3 set, dominating set, because every black vertex is adjacent to a green vertex, and the second is at the distance 3. Here is such vertex. I have this vertex marked by red color. The one vertex is green vertex is adjacent, and the second is at the distance 1, 2, and 3. For other black vertices, the similar relation holds. So the subset indicated by green color is a 1-3 dominating set. But this set given on the next figure is 1-2 dominating set, because every black vertex is adjacent to a green vertex, and the second vertex is at the distance 2. For example, if we consider this vertex, then we have adjacent green vertex, and the second vertex is at the distance 1 and 2. So it's a 1-2 dominating set, but this subset also is 1-3 dominating set of this graph, because the distance is at most 3. Analogously, we can consider 1-1 dominating set. Also, we can say that it's a 2 dominating set, because every black vertex is adjacent to at least two green vertices. So we can also observe that 1-1 dominating set also is a 1-2 dominating set, and also is a 1-3 dominating set. So the following relation holds. And Hedetniemi and in mentioned earlier paper proved that every dominating set having at least 2 vertices is a 1-4 dominating set. This means that considering 1K dominating sets make sense if K is equal 1, 2, or 3. If K is equal 1, I recall, then we obtain 2 dominating set. So it's natural, firstly, to study 1-2 dominating set. They prove that for an arbitrary graph G, such that dominating number is greater than or equal to 2, holds the following string of inequalities between parameters of domination. Clearly, classical dominating number is equal to 1-4 dominating number. It follows from the above theorem. And next, we obtain 1-3 dominating number, 1-2 dominating number, and 2 dominating number. And they show that there is a graph such that all inequalities in the string 1 are different, are strong, so all parameters are different. Let's consider our example, and in this graph we can indicate parameters related to dominating set, one free dominating number, one two dominating number, and two dominating number, such that all these parameters are different. I have some problem with our slides, so I have to show in such way, so it's a problem for me, a small, sorry. Firstly, if we consider subset C, F, I, then this subset is a minimum dominating set, so the dominating number is realized by this subset and is equal 3. The next case, we have one free dominating set. As you can see, vertices C, E, G, I belong to one free dominating set. It's easy to observe that is a one free dominating set. For example, if we consider the vertex A, then it's adjacent to a green vertex C, and the second vertex is at the distance 3, 1, 2, 3. In next case, we have 1, 2 dominating set. Also, vertex A is adjacent to C, and the second is at the distance 2. It's the distance between A and D. And the last case, we have a 2 dominating set, and this set is given by vertices A, B, D, F, H, J, and K. So we have a graph such that all these parameters are different. Clearly, we can also give an example of graphs such that all these parameters are the same. It suffices to consider a cycle with 4 vertices, then all these parameters are equal to 2. Okay. Parameters of related to 1, 2 dominating set were studied together with Adrian Michalski, Magda Derlaw, and Magda Lemańska. And in mentioned here papers, you can find, I hope, some interesting results. Clearly, I only mentioned about selected relations between parameters of domination and 1, 2 domination. I show some construction of graphs, and I show directions of our research. Clearly, for some basic graphs, we can calculate, we can determine 1, 2 dominating number exactly. For example, in path, we can find this number, it's not a problem. Analogously for cycle, we can also determine the parameter of 1, 2 dominating number. But generally, the problem is complicated. You can only observe that 1, 2 dominating number for cycle is equal to dominating number. These results are rather obvious. For an arbitrary graph G, we can observe that dominating number is less than or equal to 1 to dominating number. And this observation follows from the definition of these graph parameters. But we can find a graph such that the difference between these parameters can be is arbitrarily large. So this difference can be arbitrarily large. And I would like to show you the construction of a graph such that this difference is equal to an arbitrary integer. So to obtain such construction, we start with a star with n leaves. And here we have the case if n is equal 5. So we have a star with 5 leaves. And next, in each vertex, we insert a new star with 5 leaves, as on this picture. And next, on each edge joining central vertices of the star, as on our figure, we insert a new vertex. And then you obtain a graph G. This case, as I have mentioned, is for n equals 5. And in this graph, we determined one to dominating number and dominating number, and we show that the difference is equal to n. Clearly, in our case, it's equal 5. So on our picture, we indicate dominating number, and it's realizes by dominating number is realizes by set marked by green color. It suffices to take central vertices of our star. So dominating number of this graph is equal to n plus 2. And next, if we add blue vertices, then we obtain one to dominating number, and this number is equal to 2n plus 1. Clearly, if we look on this picture, we have here dominating set, but this subset is not one to dominating, because if we take, for example, a black vertex being a leaf, then we have adjacent vertices in this vertex, and the second is at the distance 3. So it's not a one to dominating number. So we have to add additional blue vertices, and then we obtain one to dominating number equals to n plus 2. So the difference is equal to n. And also we show that for upper one to dominating number, the difference between upper one to dominating number and upper dominating number also can be equal an arbitrary integer. And I show the construction of a graph such that such a relation holds. We start also with a star, now with n plus 1 leaves. This example is given here. We have 2 for 8 leaves, and next we add in each leaves a triangle as on our picture, and then we obtain a graph G. And in this graph, we find a set which realizes upper dominating number. It suffices to take a central vertex of this star and a vertex from a triangle as on our figure. Then upper dominating number is equal to n plus 2. Clearly, this set is not one to dominating number, because if we consider the second vertex of this triangle, for example, this vertex, then it's adjacent to a one green vertex, but the second is at the distance 2. But this subset is not a maximum minimal one to dominating set. We can find another one to dominating set with largest cardinality. And if instead of central vertex we have vertices from our triangle, then we obtain upper one to dominating number equals to 2n plus 2. So the difference between these two numbers is equal n. But as you can see, the subset which realizes an upper one to dominating number also is to dominating, because every black vertex is adjacent to at least 2 blue vertices. So instead of upper one to dominating number, we can consider upper two dominating number. So this observation also was a motivation to study a special subclass of one to dominating set, such that the parameter 2 will be attained. And Adrian Michalski introduced so-called proper one-to dominating set. And next, these sets were studied together with Magda Detlaw, Magda Lemańska, and some variants of proper one-to dominating set with also restriction of independence was studied earlier by together with Ula Bednarz. So I recall the formal definition, but firstly I show relations between one-to dominating sets and two dominating sets. Let's consider the family of all one-to dominating sets, and we know that this family includes the subfamily of two dominating set. So we want to consider such one-to dominating sets which are not two dominating set. So if we delete from our consideration two dominating sets, then we obtain a so-called proper one-to dominating set. And the formal definition is such that a proper one-to dominating set is a one-to dominating set which is not one-one dominating. So because the vertex set is a one-to dominating set because it's a two dominating set, we cannot consider the vertex set as a proper one-to dominating set. So firstly, we can ask about a graphs without a proper one-to dominating set. So firstly, we have to consider the problem of the existence of a proper one-to dominating set. And we solve this problem, namely, we prove that the connected graph G has a proper one-to dominating set even only if a graph G is not a complete graph. So next also we study parameters related to a proper one-to dominating set, clearly with the general assumption that a graph G is not a complete graph, is a connected and not complete, because then every such graph has a proper one-to dominating set, so we can consider parameters related to a proper one-to dominating set. And we prove some relations between one-to dominating number and the proper one-to dominating number. And for example, we show that that for an arbitrary connected graph without triangles, the following equality holds. So this means that a proper one-to dominating number is equals to one-to dominating number. Moreover, we show the following string of inequalities. Firstly, we have dominating number, one-to dominating number, proper one-to dominating number, upper proper one-to dominating number, and upper dominating number. So we can also give example of graphs such that all these inequalities are strong, and such graph that these numbers are the same. We have to mention that in our string of inequalities, upper dominating number does not appear because we cannot give relations between upper dominating numbers. There are graphs such that upper dominating number is greater than one-to dominating number, and conversely. So we have such example of graphs in which upper proper one to dominating number is greater than upper dominating number, and graphs in which upper dominating number is greater than upper proper one to dominating number. For example, I show only a special construction, one construction, such that all these parameters are the same. But as I have mentioned, we can give different construction of graphs related to string of inequalities form, as I have mentioned earlier, to show that there exists a graph such that all these parameters are the same. We find the following construction. We start with n complete graphs with n vertices. On our picture, we have the case if n is equal to 4. So we start with 4 complete graphs with 4 vertices, and next we add edges in such way that vertices, for example, denoted by 1, 1, 1, 1, adjoin each other. So we obtain a graph as on this picture. So in this graph, all these parameters are equal 4 because we have the case if n is equal 4. I would like to say at the end of my talk about another new type of one-to dominating set, namely perfect one-to dominating set. Because if we consider one-to dominating set, then we know that the second vertex can be at the distance at most 2. If we consider proper one-to dominating set, then we know that there exists a vertex such that at least one vertex such that the distance 2 is attained. So there exists the second vertex being at the distance 2. So now we consider a special case of a proper one-to dominating set such that this relation holds for every vertex not belonging to a proper one-to dominating set. So we consider a subfamily of one-to perfect dominating sets, shortly denoted by 1-to PDS. So I give the formal definition that the subset D is a perfect one-to dominating set, shortly 1-to PDS, if D is a proper one-to dominating set, such that for every vertex not belonging to the set D, there is a vertex in the set D such that the distance between them is equal to 2. So here we have a simple example of graphs in which we can find 1-to PDS. So every black vertex is adjacent to a green vertex, and the second vertex is at the distance 2. And such situation holds for every vertex not belonging to our 1-to PDS, so for every black vertex. So if we consider this black vertex, then we have the same situation. One green vertex is adjacent and the second is at the distance 2. The next black vertex, one is adjacent green vertex and the second is at the distance 2. And for the last black vertex, we have the same situation. So the parameter 2 is attained for all vertices not belonging to one-to dominating set. So I come back to our illustration. If we consider proper one-to dominating set, then such a situation have to hold for at least one vertex. If we consider a perfect one-to dominating set, then such situation have to hold for every vertex not belonging to our dominating set. So problem of the existence of one-two dominating sets in a graph seems be difficult. It's not, as I have mentioned earlier, if we consider a proper one-two dominating set, then we gave a complete characterization of a graph with a proper one-two dominating set. If a graph is connected, it suffices that it's not complete. But if we can consider a perfect one-two dominating set, then the problem is more complicated. So, for example, here we have a cycle with one-two perfect dominating set. Analogously as earlier, black vertex is adjacent to a green vertex, and the second is at the distance 2. Analogously, this black vertex is adjacent to a green vertex, the second is at the distance 2. So this graph has a one-two perfect dominating set. On the next picture, we indicate one-two dominating set, which is not perfect, because this black vertex is adjacent to two green vertices. So the question is about graphs with one-two perfect dominating set. At this moment, we have some partial results. As I have mentioned earlier, the problem seems difficult. We know that a graph does not always have a one-two perfect dominating set. Some interesting results were obtained recently by Ula Bednarz and Mateusz Pirga, and they studied case of graphs in which there exists a vertex of a large maximum degree. So I show only their results for maximum degree delta equals n-1. They proved firstly the necessary condition, namely if a graph G has 1-2 PDS, then G has the unique vertex of maximum degree. So we know that if such subset there exists, then the vertex of maximum degree equals to n-1 is unique. But it was proved that if we have such assumption that in a graph there exists the unique vertex of maximum degree delta equals n-1, then they proved that graph G has a one-two perfect dominating set even only if the vertex of maximum degree is a CaRT vertex. And for example, if we come back to our previous theorem, we have here a star. There exists a one vertex of maximum degree. So this graph has a perfect one-two dominating set. It suffices to take a central vertex and arbitrary leaves. Then every vertex is adjacent to one vertex, and the second is at the distance exactly 2. Here we have such example that there are two vertices of maximum degree equals n-1. Here n is equal 4, and this graph does not have a one-two perfect dominating set. And the next theorem gave a complete characterization of graphs with one-two perfect dominating set. It suffices that this vertex is a CaRT vertex. So if we consider our star and if we delete the central vertex of the star, then we obtain a disconnected graph. Also for other cases of graphs with maximum degree were obtained by Ula and Mateusz. They considered the case if delta is equal n-2, then we know that then the graph can have more than one vertices of maximum degree, but results are more complicated than the case if delta is equal n minus 1. So I will not present this result, but I hope that they also consider the case where delta is equal n minus 3 and so on. So the problem of the existence of perfect one-to dominating sets seems difficult, but at this moment we can only partial results related to this topic. So thank you for your attention, and sorry for some problem with my presentation because I cannot click the following slides. So I'm so sorry. Thank you very much.
Thank you very much, Iwona. Do you have any question or comment? No. In the social networks, not there are any question, Julian?
Nope.
No. I have some comments about the Magnet Lab for very nice talk, and the others. Not comments, question. Rita, thanks, Iwona.
Thank you very much.
Okay. I wait 1 minute. 1 minute for the question. Julian, thanks, Iwona.
And no questions on YouTube, Nate.
YouTube, okay. Next, the following about the schedule of the CaRT. I invite you to follow in the social networks, especially in YouTube and Facebook. In YouTube, I have 3 video talks. The first is about computational complexity of a host construction of symmetric cycles. And the other is graceful labelings of graphs and kernel in token diagrams. For today, it's all for the invited speakers. Rita, yes, Sarah?
Wait. Yes, Nate, thank you. Thank you to both and the rest of the participants. And so we will see tomorrow at the same time. And I hope we have better connection, some of us.
And please don't forget to like and subscribe to our YouTube channel. It's you can find us on YouTube as CaRT Combinatorics and Related Topics, and on Facebook with the same name, CaRT Combinatorics and Related Topics, where the contributed talks will appear at 12, 12 and a half, and 1 on Mexico City, or in 10 minutes, half an hour and an hour in every time.
Okay.
So I think that's all for
thank
today.
you. See you tomorrow. Mhm.